Hello everyone, I am Pragya Srivastava. I am here to record a lecture on VLSI technology. The course code is KEC 053 and the complex topic which we are going to study here is Czochralski's crystal growth. So, what is actually crystal growth and why we are here to study Czochralski's crystal growth? It all started from IC fabrication. IC fabrication is a process where we realize an integrated circuit just starting from the raw material which is available in nature, that is nothing but the silicon. So, coming on to the slides, we can see before we start, we have to discuss what is the history of electronic devices. As far as the history of electronic devices is concerned, we started way back in early 19th century where the vacuum tubes were used as a first electronic circuit. Electronic circuit, when I say, I mean to say that let's say we are talking about a transistor which is an electronic circuit, we are talking about BJT or MOSFET. So, we are talking about a transistor which can act as a switch, a transistor which can act as an amplifier. So, all the electronic circuit, electronic chips would need this switching activity to achieve certain functions. So, to start with, we see that down the line of 20 years, the next big thing which came into the market was MOSFET and then MOSFET. This MOSFET and MOSFET, here was the first time when the word transistor was coined. So, for the first time the word transistor was coined, and we can see that it delivered high reliability and low power. So, this is what we want. We want our circuit to consume less power, we want our circuit to dissipate less power, at the same time we want this to be highly reliable. Again, it took another 30 years to switch from the basic and the most primitive transistor, that is MOSFET to BJTs, which is bipolar transistors. So, bipolar transistors, we have bipolar junction transistors, we have BJT. So, when we realized bipolar junction transistors, we said that it is a era of solid state circuits. So, solid state circuits, and when we are having number of transistors fabricated on a single chip, when we are having number of transistors fabricated on a single chip to achieve a given task, we call this as IC. So, this is a IC which performs number of tasks, and then we will be having a common platform on which we can realize many functions. Just like we want to add two numbers, so we need a adder. Just like we want to multiply two numbers, we need a multiplier. So, here we have taken all total of 30 years to land up from the basic and the most primitive transistor to the modern BJT. Telling BJT as modern in today's era will not be a correct statement. So, the most modern devices which are available today, they are like nanowires, and we have tunnel FET. If we can step down to just one level, we have CN FETs, and then we have FIN FETs. So, these are the modern devices, modern ones. So, before this modern devices came into picture, we were having BJT, or we also had FET, field effect transistors. So, what is happening when we are switching from diode to MOSFET to MOSFET to BJT? We are already trying to increase the reliability. At the same time, we are switching from large scale integration to very large scale integration to ultra large scale integration. So what is integration, and what is large scale integration, what is very large, what is ultra large? So when we are integrating, means we are putting together more and more number of transistors. So this activity of putting together more and more number of transistors is increasing. So the integration is increasing. So when we say the integration is increasing, we only mean to say that the density on one single chip is increasing. Density as in number of transistors. So we have to accommodate, or we are accommodating more and more number of transistors on one single chip. So what is the one shot idea behind this? The idea is to have a IC which could perform more and more number of functions, to have an IC which is multitasking. At the same time, the same IC should add also, subtract also, multiply also, divide also. So the same IC should be multifunctional. So I want to integrate it in that case. So going from large scale to ultra large scale, it means I'm increasing the number of transistors on the same IC. This is nothing but integration. So when we talking about integration, we say that we have to have a high speed. When we are attaining some benefit, we cannot afford to lower down the speed. So I cannot buy a phone which like performs multiple functions. I can set up an alarm also, I can use location also, I can use internet also, and at the same time my phone takes 4 days to charge. So that is not required, that is not anyway will not help me. So I want it should be high speed also, and despite of charging also, I don't want my phone to open up and give me the results in like more than 1 minute. I want to open the calculator and get the results as even like in nanoseconds. So this is high speed. Low power, it should not consume more power, it should not dissipate more power, and then high integration is always there. So this three is only and only improving. So this was all about the history of electronic devices. So in the present topic, which we are talking about crystal growth, we are talking about this transistor. We are talking about transistor, and this transistor is a silicon based transistor, which is a end product. And what is the raw product? The raw product which we have in the nature is silicon. The raw element which we have for transistor is silicon. Now from this silicon, how can I get the transistor? So for this process, we are going to study Czochralski's crystal growth. We will use the silicon and we will make a wafer, and this wafer will give me a transistor, and here we have Czochralski's crystal growth process. So when I want to study the process where a raw silicon can be converted into a wafer, and this wafer can be used to realize a transistor, I want to know, I want to read, I want to have the complete knowledge of Czochralski's crystal growth process. So coming on to the topic, in 1965, Jordan Morey observed that the plotting number of transistors can be more economically manufactured, and a chip gives a straight line on a semi-logarithmic scale, meaning when the number of transistors were observed, the increase in number of transistors were observed as far as we are going ahead in years and months. So it was seen that after every 18 months, there is a just the count would increase by double. So this is what, nothing but Moore's law. Moore's law is driven primarily by scaling down the size of transistors to a minor extent by building larger chips. So the level of integration we have seen in previous slide also. The level of integration has switched from large scale to very large scale to ultra large scale. So here also we can have small scale also, small scale integration also we can have. So small scale integration would have only 10 number of gates. Medium scale integration we have 1000 gates. Large scale we have 10,000 gates. So we can realize that how level of integration was increasing when we were comfortable to increase the density. This has always already been covered. We are actually trying to see that the process of integration where the miniaturization and hence the increase equipment density, batch processing resulting in cost reduction, improved system reliability. These are all the benefits of having integrated circuits. Better functional performance, mass devices. A IC can be classified on the basis of their chip size, as we have already studied in the previous slide. This is a basic picture of IC. Here we can see an integrated circuit is a miniaturized low cost electronic circuit consisting of active and passive components fabricated together on a substrate. Coming on to the process of Czochralski's integration process. Here we can see, here it is a real time diagram where we are having these wafers. These are the wafers we see. Here these are the wafers, and we will start from raw silicon. We will start from raw silicon, and from raw silicon we will see that how a wafer is prepared, and then we will see how this wafer helps in achieving a transistor. So the CZ process is here. CZ processes here we have to study. Overall we can start from having crystals. Here is, we can see these are the crystals. When we are having these crystals and we are following this process, this complete crystal growth is CZ process. Let's say we have studied what is CZ process. We have attained what is, we have studied and we have got the final and end product. We will be having a single ingot. After the CZ process, the end result, the outcome and the obtained physical entity of CZ process is a single crystal ingot. This is a single crystal ingot here. Okay. Now after that single crystal we have got, we will make and we will make the crystal trimming. The surface is trimmed out and we have two notches here, which is crystal trimming and diameter grind. And next, the flat grinding is nothing but on one single surface we will make it flat. We will not leave it in a perfect circular cross section. So we will make it a flat out of it. So this is flat grinding, and then we will use diamond cutters. We will use diamond cutters for wafer slicing. So what we do, we slice all the wafers and get the number of wafers out of one single ingot. Here we are doing edge rounding. Edge rounding is done across the periphery. Then we are doing the lapping. On this lapping, we do it on the top and the bottom of the wafer so as to maintain the surface smoothness. We also do wafer etching to remove the oil spots, to remove the impurities which enter into the picture after the wafer has been handled a many number of times. So this etching provides cleanliness and it adds up to the efficiency in multiple folds. Then we will polish it, and then next is wafer inspection. So we have seen how we have started from a raw silicon which we have which we are presently having in the crucible, and then we are seeing how the raw silicon has been converted into wafer. This is the real picture of this ingot, and we can see that the ingot can be seen, and this is the process of lapping going on here. Here the silicon ICs are created by large circular sheets of silicon called wafers. So here we can have an idea of diameter. It is 100 to 300 mm thick, mm diameter, and the thickness is 0.7 mm thickness. So any silicon IC is approximately 1 centimeter on a side. So many ICs can have many ICs may be driven out of one single wafer. So location of ICs on a wafer is called die site. We can see that here it's a silicon wafer, and we can roughly create and imagine how the number of die sites we are having, how many number of die sites. So die sites are nothing but the sites from where we can have an IC. So wafer, one single wafer will give us n number of ICs. This is the pictorial representation of the lab setup, where we can see that after the Czochralski's process is complete, here the man standing next to it can be seen that the height or the depth of the ingot is almost comparable to the person standing next to it, and it is even more. Coming on to Czochralski's crystal growth process. What is actually Czochralski's crystal growth process? And we will see it using a clear one-shot diagram. So in Czochralski's crystal growth process, we will have to see the apparatus. In this apparatus, we can see we are having a chamber, and inside the chamber we are, here it is, here we can see it's an insulation chamber because the temperature inside exceeds 1200 degrees Celsius. So inside the insulation chamber, these are the heaters. Here these are the heaters. Inside the heaters we have, we also have to mention that we have an inert gas environment, and argon helps us in the same. Inside the heaters we have a susceptor here, and this susceptor holds the silicon. So as we have seen in the previous slide, we have poured silicon which is available in the nature, and due to the effect of temperature, this silicon starts melting. When the silicon starts melting, we have a picture. Here we can see it is silicon here. When we see that the silicon starts melting, we drop a thread-like structure from the top. So when we drop a thread-like structure from the top, and at the same time we are rotating the system. So what will happen? There will be a situation when after this melt is due to the ambient control and the temperature control, there is a formation and silicon starts settling around the thread, and once it is rotated, once the thread is rotated, we rotate the thread, and using this rotation, this accumulation takes a circular shape. This accumulation results in a circular shape disc in the center. At the same time, we are pulling it off. When we are pulling it off, we are getting a cylindrical structure. Here we can see that how a cylindrical structure is obtained. So this, we have to see that we should know what is the exact rotation rate, what is the exact full rate in order to have the correct size of the ingot. So as far as the apparatus is concerned, we can see that the apparatus is having crucible. It is having the silicon melt here. This crucible is holding the silicon, and then we have the crucible susceptor. Crucible susceptor is nothing but a susceptor that holds the crucible. These are the heaters. These heaters will maintain a temperature of more than 1200 degrees Celsius. And then this is the thermal insulation. This is the insulation, so that the person standing outside is not that affected. So it is the formation of single crystal silicon. We call it neck and shoulder because this is a portion where we can see a neck is called, neck can be seen, and here is the portion where we can see shoulder can be seen, and this complete thing is called ingot. This complete thing is called ingot. So this is nothing but how Czochralski's crystal growth results into a preparation of ingot. We can see here melting of polysilicon takes place. When the silicon starts melting, the level of liquid we can see has increased, and then we are dropping a thread and we are rotating also. We can see it's rotating. We are rotating also. When we are rotating, there is accumulation at the bottom, at the center, not the bottom, at the top and the center, and then we are pulling also. We are pulling also. So when we are pulling the thread, we are like pulling the thread, then this seed like structure has been obtained. Now when the seed like structure is obtained, we can see that the level of liquid is reducing and it has come down to almost minimum. So this is the overall step of Czochralski's crystal growth mechanism. We can see the first is nothing but the furnace, where in the furnace we have a quartz envelope. The overall structure which we were seeing in the previous diagram were having the quartz envelope, and the quartz envelope may be cooled. Crucible is a cup in which electronic grade silicon. Now what is electronic grade silicon? The raw silicon which is available in this nature is metallurgical grade silicon, and we treat it and convert it into electronic grade silicon, and there are set of chemical reactions. It's a chemical process where metallurgical grade silicon is converted into electronic grade silicon. After the silicon growth, when we are cooling down the system, because of the thermal mismatch, usually the quartz crucible sometimes crack. So, we cannot reuse, generally it cracks also. So, we cannot reuse the. Now, we have to study what is crystal pulling mechanism. The crystal pulling mechanism is nothing but we should have a pull rod, which after rotation it pulls also. So, the two things which we have to study is the pull rate and the rotation rate. These are the two things which are very important, the pull rate and rotation rate. Pull rate varies inversely with diameter, of course. When we are pulling it for a higher speed, the diameter can reduce. So, what happens is, if we are pulling it away faster, let's say we were pulling for a consistent amount of speed, so this was obtained. When we started pulling fastly, the diameter reduces. So, here we can see that diameter is reducing sometimes. So, this is nothing but how a pull rate is varying the diameter. Growth rate depends on the number of sites for the phase of crystal and heat transfer at the interface, and it can be greater than pull rate and even can be negative. This is another example of the Czochralski's crystal growth, and we sometimes call this jacketed crystal growth puller. So, this jacketed crystal growth puller is having a water jacket outside, which acts as a heat shield, and in addition to this water jacket, we also have a heat shield here. This heat shield is also here, which was obviously having in the previous crystal growth, which we already had in the previous setup of CZ process. This is another option which we are using just for better insulation, because the temperature inside, as I have already told you, is 1200 degrees Celsius. So, this water jacket helps. Other than that, we can see that everything remains the same. Here we are rotating and we are pulling also, and then we are getting a seed-like structure can be seen. And as far as the puller is concerned, we have the same thing, the single crystal silicon quartz tube, and there is a carbon heating element, and then we have a water jacket, molten polysilicon, and at the top we have a puller. So, we can see how the distance and this temperature has a relation. What is happening is, when we are increasing the temperature from 700 degrees Celsius and we are going till a temperature which is approximately 1500 degrees Celsius, and we can see that there is a distance. We can see there is a point A, there is a point B. So, when we started at 700 degrees Celsius, and what is actually happening is, from B we can see ki we were just at the start. At the start, when the temperature, we cannot start it from 0 and go directly to 1200, no. So, we were at nothing but 0. So, we gradually came down to 100, 200, 500, 700. So, when we have got this 700 temperature, 700 degrees Celsius, 700 degrees Celsius, there was a start of formation of seed, and then as and when we increase the temperature, we get a uniform crystal. So, as the temperature increase, we have a increase in number of interface. So, in between, let's say we have points x1, x2, x3, we'll be having here x1, x2 and x3. So this was all about on Czochralski's crystal growth from my side. We will start again an introductory and an informative session on another complex topic. Thank you.